Okay, the next is standard reduction potential, SRP, in case of D block elements. Okay, standard reduction potential or SRP. Ready? Actually, you know, if I have a M the solid, which become M2 plus aqueous. M2 plus aqueous. Then what is the potential difference between M and M2 plus? That is said to be standard reduction potential, which means that I have a M2 plus aqueous solution, M2 plus aqueous solution, where M the solid is placed. Okay, and it is discussed in electrochemistry. Then there creates a electrical double layer between these two, or there forms a potential difference between the M2 plus and M. That what we called as electrode potential or reduction potential. Okay, so let's check the trend of reduction potential of M2 plus to a divalent positive ion to M, okay, or the electrode potential between these two. Ready? So listen, this electrode potential that is proportional to the energy change for this conversion. Okay, this conversion have some kind of energy change, and what is the energy change? That is exactly proportional to the electrode potential. So let's have a discussion about the energy change in that case. Okay, so I want to show the reaction M2 plus M become M2 plus aqueous. For that, your M solid needs some sublimation energy to become what? Gas. Then it have to ionize, followed by it have to hydrate. You know what is the meaning of aqueous? M2 plus ion, which is surrounded by a number of what? M2 plus ion is surrounded by a number of water molecule. That is what we called as M2 plus aqueous, or M2 plus is hydrated. Okay, so starting from M, first of all it absorbs some kind of energy to turns to a gaseous state, what we called as sublimation energy, followed by the first ionization energy, the removal of first electron, to become what? M plus gaseous. Then the removal of second electron, IE2. Ready? And it become M2 plus gaseous. Ready? Then which is placed into water. Ready? And M2 plus gaseous ions, when it enters to water, it's surrounded by water molecule, what we call as hydrated. Okay, then they release an energy said to be hydration energy. Okay, if water molecules are surrounded by the M2 plus ion, what happen means the M2 plus obtain an extra stability, or M2 plus acquires a extra stability. Okay, so stability of M2 plus increases once the water molecules surrounded the M2 plus or hydrated. Ready? Hence the energy of system decreases, which means an energy released, and that released amount of energy when an ion is surrounded by water molecules is said to be hydration energy. Okay, so due to stability, its energy of system decreases, which means a system releases energy to the surrounding, and that energy is always negative, which is said to be hydration energy. Ready? We know that energy required to convert a substance from solid to gas, that is called sublimation energy. This is always a positive value. This is always a positive value. Okay, you have to supply energy, then only it becomes solid to gas. Ready? Whereas you know ionization energies are also positive. Ready? This is positive and this is also positive. The only energy term in the conversion of M solid to M2 plus aqueous is with the negative value is hydration energy. The only term which having a negative value in this conversion is hydration energy. So already told you that the change in enthalpy of this reaction, this conversion, that is proportional to the electrode potential. that is proportional to the value of electrode potential. Ready? Higher the change in enthalpy, more positive is the change in enthalpy, then more positive will be the electrode potential. Is it okay? More negative the change in enthalpy, or relatively lower. Higher value means it become more positive. Lower value means it become more negative. Higher the value, which indicates that electrode potential is also higher. Lower the value, which indicates that electrode potential is lower. Ready? So from this conversion, you have to know the main point is that the change in energy that is proportional to electrode potential, or that is proportional to EM2 plus bar M. Ready? Fine. Moreover, if high value of delta H, high value of delta H, if the delta H have high value, more feasible the reaction, which means the reaction is, what is the reaction? M2 plus more feasible will be the reduction. M2 plus 2 electron gives M. Okay. So higher the value of delta H, more feasible will be the reaction. If the electrode potential is corresponding to this reaction, right? This is a reduction potential, and the reduction potential is corresponding to this reaction. Ready? M2 plus 2 electron gives M. Okay. Higher the electrode potential, which indicates that more feasible will be the reaction. Okay. Higher E0 value means more negative will be the delta G. Delta G, you know the relation between delta G and E0 are negative relation. Higher the potential means more negative will be the delta G, more feasible will be the reaction. Okay, so higher the value of this reduction potential, that indicates that M2 plus have a ready tendency to become M. M2 plus have a ready tendency to become M, which means that relatively M will be more stable than M2 plus. Okay. A have a ready tendency to become B means which one is more stable? B is more stable, like that. If M2 plus have a ready tendency to become M, which indicates that M is relatively more stable than M2 plus, or the reverse is also possible. Reverse is also possible. Okay. So if high value of delta H means high value of E0 M2 plus bar M. Okay, then more feasible will be the reaction, which means that M will be more stable. M will be more stable. Ready? Higher this value, how it become a more positive value? How the delta H become a more positive value? This positive values or this positive magnitude should be much greater than the negative hydration energy. Then only the net value become positive. Then only the electrode potential become positive. Then only the point is okay. Ready? Fine. And the reverse is also possible. Ready? If low value of delta H, that indicates that low feasibility or less feasibility for a reaction. Okay, so which indicates that M2 plus aqueous is more stable. Okay, M2 plus aqueous is more stable. Okay, right. That's all about the ideas. Now we can we have to apply this concept in some cases. Okay, why the value of E0 Zn2 plus bar Zn is low, the value of M2. So questions may ask like this. Okay. So standard reduction potential, standard reduction potential. But the first one, trend in M2 plus bar M. Okay. You can show this one. Okay, where the delta H is actually, according to Henry's law, delta H is actually delta sublimation enthalpy plus delta IH1 plus delta IH2, sum of first and second ionization enthalpy plus delta hydration energy. Okay, this much will be positive, this will be the negative. Okay, so that positive and negative value decides the net value.
There may be some questions or some points which are regarding this one. That is, generally from left to right, in a general version or general case, from left to right. From left to right means we have to discuss this in 3D series, okay? 3D series. And you know the 3D series, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, okay? There are some questions based on this one. Scandium usually highly unstable state. Scandium for the +2 is highly unstable. Okay, ready. So there is no discussion about the E0. There is no discussion about E0, Se2 plus bar, Ac, because scandium the most common oxidation state is +3. Okay, +2 relatively unstable. So we are discussing from here. From here to here, the +2 is a common oxidation state. From titanium to zinc, the +2 is a common oxidation state. Fine. In a general case, from left to right, electrode potential become more positive. Here is negative, or moving left to right, it is more positive. The necessary explanation is nothing but on increasing the ionization energy.
We know that from left to right ionization energy increases. Ready? So ionization energy increases means what happens? If ionization energy increases, the positive value become increases. If the positive value become increases, then reduction potential increases. Okay, so that's the first point. Ready? Got it? First point. In 3D series, from Ti to zinc, titanium to zinc. In 3D series, from Ti to zinc, E0 M2 plus bar M, E0. In 3D series, from Ti to zinc, titanium to zinc, comma, E0 M2 plus bar M, M2 plus bar M, become more positive. Okay, just put an explanation in the bracket. Due to increasing sum of or due to increase in ionization energy. Okay, due to increase in ionization energy. So ionization energy tend to increase or tend to make the value more positive, right? Ready? Fine. But there are a lot of exceptions. Ready? E0 Mn2 plus bar M is low. It's comparatively low. Ready? Low means from here to here it become more positive, but in case of manganese it become much negative. Like that, this is comparatively more negative value. We want to have an explanation about that. This is exceptionally a positive value, plus 0.34. Okay, there is an explanation, and this is also having low value. From left to right, the trend is generally increasing, but here also the value is negative. Okay, the explanation is based on this one. Already told you that if the value of delta H is, or if the value of delta H means E0 M2 plus bar M is more means what? More positive. Then the explanation M will be more stable, like that. Okay, or M2 plus is relatively unstable. M more stable means M2 plus relatively stable. Okay, or any other kind of explanation. Or if the value is low means negative. If the value is low, which means negative. If it is negative, then M2 plus will be more stable. That is a point. Okay, so first explanation, why the E0 Mn2 plus bar Mn and E0 Zn2 plus bar Zn is much low means, or more negative means. We know that Mn2 plus is stable, right? M or Mn2 plus is more stable. What about the configuration of Mn2 plus? Mn2 plus is argon 3d5. Argon 3d5 have half filled stability. Ready? What about Zn2 plus? Zn2 plus argon 3d10. Okay, so the value of Mn2 plus bar Mn and Zn2 plus bar Zn, why it become more negative means it is due to the stability of M2 plus. Ready? So the first point. E0 Mn2 plus E0 Mn2 plus E0 Mn2 plus bar Mn. E0 Mn2 plus bar Mn. Mn2 plus bar Mn and E0 Zn2 plus bar Zn are exceptionally low in bracket negative. Low means what? Negative. Okay, and the explanation is based on the stability of, okay, it is based on the stability. Concept is okay. Ready? If it is low means M2 plus is, the reaction is less feasible, which means M2 plus have no tendency to become M, which means M2 plus is stable. Okay, because reason, put the reason. Mn2 plus 3d5 and Zn2 plus 3d10 have stability. So that's the reason, okay. Mn2 plus is 3d5, whereas Zn2 plus is 3d10. They have stability. That's the reason. Ready? Fine. So the next point, why the nickel have a more negative value, or relatively from left to right the value should have to increase, but nickel shows a negative or much negative value comparatively. Why it become means the sum of ionization energy of nickel, it is not compensated the hydration energy, or hydration energy of nickel is much negative, or nickel have a large hydration energy. So the released value, the negative value will be dominant comparing to the ionization energy. Okay, so the net change will be a negative. That's why the electrode potential of nickel is negative. Okay, so why the nickel have a negative value means it is not due to the based on stability. It is not based on stability. It is based on hydration energy. Okay, so fine. Next one, E0 Ni2 plus bar Ni. E0 Ni2 plus bar Ni. E0 Ni2 plus bar Ni. E0 Ni2 plus bar Ni, low bracket more negative, low bracket more negative due to much negative hydration energy or large negative hydration energy. Okay, and why it is negative or why it is low means due to large negative hydration energy. Okay, fine. Then there is an exception. The value of copper is, they all have negative value, even zinc itself. Zinc have minus 0.76, okay. Actually, the trend is perfectly shown by copper. That is, from left to right, increasing means the copper have a greater increased value, plus 0.34. Why the value of copper is positive means the sum of ionization enthalpy. We know that, listen, the second ionization enthalpy, listen, second ionization enthalpy of copper. What about the copper configuration? Copper having 4s1, 3d10, okay. So Cu plus means 4s0, 3d10. So this is first ionization energy, no problem. It makes stability, so relatively low. But what about the second ionization energy? If Cu plus become Cu2 plus, what happens? The stability disturbed, right? Okay, so this is said to be the second, and this is much high. If this is much high means the positive value is much or having a greater magnitude. So it results in the positive value of electrode potential. Okay, so that's the explanation. Ready? So the next point, E0 Cu2 plus bar Cu. E0 Cu2 plus bar Cu. E0 Cu2 plus bar Cu. High bracket more positive, high in bracket more positive. Okay, due to, or the explanation, due to greater second ionization energy, due to greater second ionization energy, due to the greater second ionization energy. Okay, exactly the very same idea we can use in the trend of this one also. Trend of M3 plus bar, M2 plus. M3 plus bar, M2 plus. The very same idea. Okay, that means we are considering the E0 M3 plus bar, M2 plus. If this value is positive means the reaction is feasible, which means M2 plus is more stable than M3 plus. The very same concept, okay. So trend of M3 plus bar, M2 plus, okay. Ideas all are same, so we can write some cases. Ready? First one, E0 E0 Sc3 plus bar Sc2 plus Sc3 plus scandium E0 Sc3 plus bar Sc2 plus low. Why it is low? This having an argon configuration Sc3 plus argon 4s2 3d. So once it loses 3 electrons, it become argon configuration, noble gas configuration, where this is not much stable. Okay, so why this value is low means this reaction is less feasible, which means Sc3 plus have a greater stability than Sc2 plus. So the explanation is based on the stability of Sc3 plus. Ready? So low, you can show you can write the explanation due to stability of Sc3 plus. Okay, the next E0 Mn 3 plus bar Mn is higher than Mn2 plus. E0 Mn3 plus bar Mn2 plus is higher than E0 Cr3 plus bar Cr2 plus and E0 Fe3 plus bar Fe2 plus. Okay, so for that we have a explanation. Why this value is much high? More positive means this reaction is feasible, right? If this value is higher means more positive means this reaction is feasible. Mn3 plus 2, Mn2 plus is feasible, which means that this is more stable. That's correct. This is 3d5. This will have a extra stability comparing to Mn3 plus. Okay? Mn3 plus have a ready tendency to become what? Mn2 plus. Whereas in the case of this one, these two values are relatively low compared to this one. Okay, they are neighboring members, chromium, manganese, iron. Okay, why means in aqueous solution Cr3 plus is more stable. That's the explanation. Where means this is in the case of aqueous solution, right? Cr3 plus is in aqueous solution, right? So in aqueous solution Cr3 plus, what about the configuration of Cr3 plus? Chromium have argon 4s1 3d 5. Once it become Cr3 plus, what is the configuration? Argon 3d 3. Okay, in aqueous solution where the Cr3 plus having electrons of 3, right? Chromium exists as an octahedral complex. What octahedral complex? In case of octahedral complex, the configurations is based on crystal field theory. I think you are familiar with the crystal field theory. The degenerate d orbital split into two, T2g and Eg. Okay, so in aqueous solution, Cr3 plus surrounded by H2O molecules and it become a complex where the actual electron is in the 3 electron. This is not half-filled stability, right? Is 3d3 is an half-filled stability? No. But this configuration is stable. Why means the T2g have 3 electrons. I think you are familiar with the T2g Eg. T2g means have 3 orbitals and Eg means 2 orbitals. Okay. In octahedral complex, the lower energy orbital is T2g and higher energy is Eg. If this have 3 electrons means this is in a perfect arrangement. Okay, so if the chromium is in +3 oxidation state, moreover in aqueous solution,
it have a octahedral geometry where the 3 electron in that +3 oxidation +3 chromium which arranged in T2G which become more stable. Ready? It's not based on half field stability, but it is based on the crystal field stability. Okay, fine. And this we know Fe3 plus to Fe2 plus, the value is low means Fe3 plus is stable. That's correct. Fe3 plus have 3d5. Fe3 plus have 3d5. Iron have configuration of 4s2. 4s2 3d 6. If it become Fe3 plus, it become 4s0 3d5. So due to 3d5 half field stability. Okay, so the concept is very same. If this is low means there is some kind of stability. If this is high, that is a concept. Okay, so you have to give a proper explanation. So this value high means this reaction is feasible. Mn3 plus have a ready tendency to become Mn2 plus, which means Mn2 plus is stable. So you have to give an explanation for the stability of Mn2 plus. Okay, whereas these two are relatively low means this reaction is not much feasible, which means the initial ion is more stable. Cr3 plus is more stable. So once we are looking the electrons of Cr3 plus have 3 electrons, then how it becomes stable means based on crystal field theory. Okay, whereas this is directly we can predict on the basis of normal half field stability. Okay, so these are the cases. Ready? Fine. So I think this point is written in the note, right? So it can show proper explanation. Ready? Okay, for your NEET examination, the questions from inorganic chemistry mainly based on your NCERT textbook. Mainly, it's nearly 95% based on NCERT textbook. Okay, so you're well familiar with the all points in your textbook. Okay, that is the thing that you have to do. But in case of organic chemistry or physical chemistry, there will be something other than your NCERT textbook. Okay. For your NEET examination, for inorganic chemistry, NCERT is enough. Okay. NCERT have a lot of points. Ready? So I'll give each and every point or almost all points. Ready? And I'll give you a proper explanation. So explanation points, you have to study that. That is the trend of inorganic chemistry. Ready? Okay. So there may be some kind of questions. Why Cr2 plus reducing agent in aqueous solution, okay, where Mn3 plus is oxidizing agent. Even both have 3d4 configuration. Even both have 3d4 configuration, okay. So this can be explained on the basis of this concept. Ready? Listen. Cr2 plus the configuration is 3d4. It's chromium, argon, 4s1, 3d5. Once it loses 2 electrons, 3d4. Manganese, argon, 4s2, 3d5. Loses 3 electron means 4s2, 3d5, not loses 3d4. So both have a configuration of 3d4. Ready? But Cr2 plus and Mn3 plus have same configuration 3d4, means same electron. Okay, then on the basis of what criteria it acts as a reducing agent and it acts as a oxidizing. Okay, reducing agent means what? Tendency to oxidize. Okay, so in solution, it is clear that in solution Cr2 plus will readily become Cr3 plus because Cr3 plus is more stable. That is already explained. Ready? So in aqueous solution, tendency to oxidize. In aqueous solution, Cr2 plus have tendency to oxidize to form Cr3 plus. Okay, this have a T2G3 stability. Ready? Whereas this one have
tendency to, this oxidizing ion means reduced to become Mn2 plus. So this, you already know that have 3D5 stability. Okay, so this is our explanation. Ready? Okay. Next point, in aqueous solution, Cu2 plus more stable than Cu plus. Cu2 plus more stable than Cu plus. Okay. Write one more point. Cu plus may disproportionate in aqueous solution. Disproportionate in aqueous solution. So Cu plus 1 may disproportionate to Cu2 plus and Cu0. Okay. So relatively less stable in aqueous solution. Okay. But in free state, Cu plus is more stable than Cu2 plus because Cu plus have 3D10 configuration. Okay. One more point. So it is observed that Cu plus undergoes disproportionation as aqueous solution, so relatively less stable. Whereas due to due to extra hydration energy, much negative hydration energy of Cu2 plus in aqueous solution, the relative stability of Cu2 plus is comparatively greater than what? Cu plus. So in aqueous solution, Cu2 plus have more stability than Cu plus. Explanation is based on two ideas. Number one, it is observed that Cu plus disproportionated in aqueous solution, which indicates that relatively less stable. Second explanation, on the side of Cu2 plus have more hydration energy. Okay, have more hydration energy. Even if its ionization energy is greater, comparatively it have more hydration energy. If Cu2 plus have more hydration energy means Cu2 plus have a ready tendency to exist in aqueous solution because it is well surrounded by what? H2O. If it is well surrounded by H2O, then its stability increases and it releases a large energy. Okay, if a species have greater hydration energy means it is more comfortable to exist in aqueous solution. Okay, so compared to Cu plus 1, Cu2 plus have a greater tendency to exist in aqueous solution. And it is based on two ideas, or the explanation based on two ideas. First one, a tendency to disproportionation by Cu plus. And the second one, much negative hydration energy or large negative hydration energy of Cu2 plus. Okay, so first one I think it is written right. The second one, Cu2 plus have large negative hydration energy. Large negative hydration energy. Large negative hydration energy. Ready? Okay. So that's all about the concept in SRP. Move to the next. Metallic bonding, melting point, comma, next heading, melting point, comma, boiling point, and heat of atomization. Melting point, boiling point, and heat of atomization. You know the concepts: melting, boiling, atomization. There is a general trend. The melting point, boiling point, and heat of atomization, that depends on the strength of bonding in your metallic crystal. Okay, if your metal exist in which have a close packed structure, you know, okay, and it may be in a HCP, CCP, BCC, like that. Okay, any kind of highly efficient close packing. Ready? And we know that each orbital have unpaired electron. D orbital have unpaired electrons for almost all transition elements. Okay, if orbitals have unpaired electron, we know that there are a lot of metal atoms which is highly packed. Ready? And this metal atom have unpaired electron in d orbital. Another metal atom have unpaired electron in d orbital. So what happened means, in between them there may be a chance for covalent bonding between metals. Ready? There may be a chance for covalent bonding between the metals since they are arranged in a nearest position, moreover highly close packed. The partially filled orbitals of each metal atoms may be overlapped to form covalent bonding. Ready? Number two, there may be a chance for metallic bonding. Metallic bonding means what? Metallic bonding means we have kernel-like setup. Write this. The outer electrons of that typical metal will be get outside from the valence shell, and there is an interaction between the rest part with the outer shell electron, and that is said to be metallic bonding. Okay, valence electron, you know, atom simply considered as an arrangement of nucleus, inner shell, plus what? Outer shell. This is nucleus plus inner shell, simply said to be kernels. And this is outer shell, where valence shell, having valence electron. Okay, usually in the case of non-metals, maybe the valence electrons are entering to the crystal lattice, and there is an attraction between the kernels and the valence electron, which is said to be metallic bonding. Okay, so there is a chance for metallic bonding and covalent bonding in a close packed metal crystal. Ready? And that depends on the availability of free electrons. Availability of free electrons, not paired electron, unpaired electron. Availability of unpaired electron. We know that from left to right, what happens? What about the availability of unpaired electron? Iron, cobalt, nickel, copper, zinc. Okay, unpaired electron. 3d1. 3d1 means 1 electron. 5 electron. Okay, say actually this is 6 electron. 4s1. Ready? And this is 3d 5. 3d sorry 3d6, where the unpaired electron is 4, then become 3, 2, 1, so on. Okay, so the availability of unpaired electron first increases, then decreases. Okay, so the strength of or the extent of covalent bonding, or the strength of covalent bonding and the strength of metallic bonding, there is a chance for metallic bonding or covalent bonding in a metal crystal. Okay, due to the presence of unpaired electron or valence electron, freely available valence electron. Okay, so there is a chance for covalent bonding, and that metallic bonding is the intermolecular force in your metallic crystal. Ready? So if the intermolecular force is higher, then melting point, boiling point, heat of atomization will be higher. Okay, so that intermolecular force, like covalent bonding and metallic bonding, or that force of attraction, that depends on the availability of unpaired electron. Okay, where the unpaired electron trend is first increases, then decreases. Okay, so the trend of melting point and boiling point and heat of atomization also follows the same. Okay, first it increases, then it decreases. Okay, there are some exceptions. In case of manganese, okay, here the yttrium, zirconium, niobium, molybdenum, technetium. In case of technetium, manganese, actually the availability of unpaired electron is 5, right? So we are expecting a greater metallic bonding in the case of manganese and technetium, but it is not observed. Why? Means this is having an extra stability, d5 configuration having an extra stability, so that d5 electron is usually localized, it is not freely available. Due to the stability, the atoms tends to keep the d5 electron having half-filled stability, right? So the atom have a tendency to keep the half-filled electron by its own. Okay, so it is not available for what? Covalent bonding or metallic bonding. Ready? Okay, so that's why there is a small exception in the case of manganese and so the graph is something like this. Ready? First increases, then have a decrement. Ready? So first point, melting point, boiling point and heat of atomization. Okay, listen, first you have to show this point, MP, BP and delta ATMH, heat of atomization, melting point and boiling point, that depends on covalent and metallic bonding. Okay, which is proportional to availability of unpaired electrons. Okay, so we can discuss the points based on availability of unpaired electron. Ready? Okay. Next point, in any series, what about the availability of unpaired electron? First increases, then decreases. That's a general trend, okay? In any series, the availability of unpaired electron first increases up to middle, first increases up to middle, then decreases. Up to middle, then decreases. First of all it increases, then it decreases. Ready? Hence the trend of heat of atomization, boiling point, melting point also follows same. Ready? It is already written. Okay. Hence the trend of heat of atomization, boiling point, melting point also follows the same. Ready? But some exceptions are there. There is a graph in your textbook. No need of studying the graph. You simply identify the concept from that. Okay. And this is for what? 5D series, and this is for 4D, and this is for 3D. Okay. This is actually manganese. This is technetium. Okay. So comparatively, and this is for tungsten. Okay. Comparatively, so the same observation is not in the case of what? 5D series. Okay. Manganese, technetium. What about the categories? Scandium, titanium, vanadium, chromium, manganese, yttrium, zirconium, niobium, molybdenum, technetium, lanthanum, hafnium, tantalum, tungsten, rhenium. Okay. So this is not actually observed in the case of rhenium. Ready? The decrement of the exception, this is the exception, right? Okay, even have maximum number of unpaired electron, its melting point, boiling point and heat of atomization is comparatively low. This is not actually observed in case of rhenium. Ready? So you can show a general trend for this graph. Okay. So the points from this graph, that is Mn and Tc have low heat of atomization, melting point, etc. due to D5 configuration. Okay, not available for bonding or available as free electrons. Okay, so that's the explanation. And one more point, it is clear that this is actually a plot between melting point versus atomic number. Okay, atomic number versus Melting point. So what about the melting point? On moving down the group, what happens to melting point? The trend is discussed across a period, right? First increases, then decreases. That based on availability of unpaired electron. Okay. So across a period, this is a trend. Okay. And there is exceptions in 3D and 4D series, but not much in 5D series. Fine. And one more point, we are moving down the group, what happens? Melting point and boiling point increases. Okay, so as the size increases, the availability for free electron will be increases. But the nucleus have a low force of attraction to the outer shell electron, so it is much available for metallic bonding. Ready? So that's explanation. So next point on down group. MP increases. MP means the all, okay? In bracket, greater the size, greater availability of free electron, greater metallic bonding. The explanation is on moving down the group, a melting point, atomization, boiling point, like that increases. Okay, the explanation, greater the size, greater the availability of free electrons, greater will be the extent of metallic bonding. Okay, so that's explanation. So that's all about the melting point, boiling point. The next, physical property. Okay, so they almost shows the property of a typical metal, like high melting point, high boiling point, high tensile strength, ductility, malleability, like that. Okay, so write down high tensile strength, ductility, malleability, tensile strength, ductility, malleability, fine. Then melting point, MP, BP. These all are relatively in comparison with S block metal. Okay, compared to S block metal. Ready? Metallic luster, thermal and heat conductivity, they all are relatively high. Okay, metallic luster, shining appearance of a typical metal. Ready? But exceptions are there. In case of your 12th group, okay, zinc, cadmium, mercury, they all have exceptions. Conductivity, heat, thermal and both are same. Thermal and electrical conductivity. Okay. Thermal and electrical conductivity. Ready? Okay. But zinc, mercury, cadmium are volatile. So volatile means easily vaporizing tendency, which means the molecular force of attraction all are weak. Okay, so melting point, boiling point, like that, all properties are entirely different. Volatile, and they have typical closed factor structure or crystalline structure. Typical crystalline structure. In bracket other than HCP, CCP, BCC, other than HCP, CCP, BCC. Okay, all the remaining can show HCP, CCP like that. Okay, but in addition to HCP, CCP, your zinc, cadmium, mercury have a typical another crystalline forms. Okay, so they are entirely different. You know the reason, due to the presence of filled d orbital. That's the reason. Okay, the property exception is due to that one. Okay, one more point. Mercury have low melting point, whereas tungsten have high melting point. Okay, element with the low melting point is Hg, whereas tungsten have the high melting point. So that's all about the discussion in your melting point, boiling point, physical property like that. So that's also over. The next, the topic. Next, the topic is magnetic property. Magnetic property. Oxidation state and the stability of halide oxide, it is remaining. The next topic, that is magnetic property. Okay. Magnetic property. And you know, transition metal shows high magnetic property is based on the presence of unpaired electron. Okay, so first point, they can show paramagnetism or diamagnetism. They can show paramagnetism or diamagnetism. And the strength of magnetic moment. You know, paramagnetic, diamagnetic materials are weakly attracted by external magnetic field is said to be diamagnetic. If it is strongly attracted, ferromagnetic. Weakly repelled, paramagnetic. So they are belongs to diamagnetic, paramagnetic or ferromagnetic. Okay. And the strength of magnetic moment or magnetism. Strength of magnetism depends presence of unpaired electron. The strength of magnetism depends presence of unpaired electron. Okay, presence of unpaired electron. So there is a formula for finding a magnetic moment. So spin-only formula. Spin-only formulae. That is mu is equal to root of n plus 2. Okay, or mu is equal to root of 4s into s plus 1, where s is the n into half, summation of spin. Summation of spin. Okay, where the unit is Bohr magneton. Bohr magneton. And one Bohr magneton is actually 9.27 into 10 to the power minus 24 ampere per meter square. Okay, where you know the n is number of unpaired electrons. Okay, so here the chance for number of unpaired electrons in case of d block element is, it may be d1, d2, d3, d4, d5. Okay, And you may ask to find the magnetic moment. And the magnetic moment in Bohr magneton, if n is this is configuration. Okay, here the magnetic moment, or here the n value, here the magnetic moment in Bohr magneton. If d1 means 1, so what root 3 will be the answer, 1.7. If d2 means 2, 2.84. Okay, 3, 3.87, 3.87, 4, 4.90 or 9, ready, 5, 5.9. So it is clear that the first value, that is exactly same with the number of unpaired electron. Okay, if n is 1, what is the answer? Root of 1 into 1 plus 2, root 3, 1.73. If n is 2, root of 2 into 2 plus 2, root 8, root 8, root 9 is 3, root 8 will be 2.84. Okay, like that, if you are solving using this equation, this will be the value. This is fixed, always fixed. Okay, so if ion M3 plus ion, M3 plus ion, you don't know the ion, having a magnetic moment of 4.9 means you should know that it contains 4 unpaired electrons. Okay, or if you are asked to find the value, if you know that there is 4 unpaired electrons, then it will be 4.90. No need of finding the root from there. Okay, so this is important, keep it in your note. Okay, write some question. Find magnetic moment of M2 plus. M2 plus. Find the magnetic moment of M2 plus. M, where M is a general symbol. Okay, it's not manganese. M2 plus. In bracket, Z equal 27. Atomic number is 27. Okay. So if the atomic number is 27, you have an expected electronic configuration. Okay, by losing 2 electrons, you obtain the number of unpaired electrons. So that will be the answer. Okay, if you have number of unpaired electrons, you can easily find the magnetic moment value. Unpaired electrons. M, the configuration is 27. So argon 4s2 27. If it is M2 plus means electron will be argon 3d7. If 3d7, and for D1 and D9, right? For D1 and D9, the value of n will be 1. Okay, what about the D9? D9 will be this one. So for D9, the n value will be 1, and D1 also, n value is 1. Okay, so for D2 and D8, the n value will be 2. For D3 and D7, the n value will be 3. For D4 and D6. Okay, so here we have D7. So 10 minus 7, that is n equal to 3. So answer will be 3.87. Ready? Find the value. Enough.
First one CO3 plus. Cobalt having 27, right? Cobalt is 27. 3 plus means? N, I want the value of N. 4. Mn2 plus N is 5. Okay. Fe2 plus 3d6 is the configuration. 3d6 means 4. Okay. Cr3 plus we know 3d3. It is already discussed. Okay. 3d3. So 3. Fine. So that's all about the magnetic moment. Okay. They may ask to find a magnetic moment. And what about this equation? What about this equation? If I have CO, these two are same. Okay. So no need of finding a question for calculating the spin on a magnetic moment in terms of this one. But you have to know this is also an equation. If they are asked in terms of this expression, if the choice is in terms of this expression, so you have to know this is also used for finding magnetic moment. Okay. If you are asked to find the magnetic moment, you can use this one or this one. Both are same. Okay. But you have to know this is also an expression for finding the magnetic moment. And how we can do a problem in this using this equation means, if I have CO3 plus means 3d7. 3d7 means, I'm sorry, 3d7. This is the 3d6. Okay, 3d6. 3d6. Okay, 3d6. Right. So n is 4. Okay. So S is equal to 4 into 1 by 2. 2. Okay. So mu is equal to root of 4 into 2 plus 1. 8 into 3, 24. Root 24 is 4.9. So then the very same answer. Okay, both are same. Okay, so no need of finding a magnetic moment in terms of this equation. But you have to know this is also an equation for finding magnetic moment. Okay. Enough. So moving to the next, catalytic property. Catalytic property. Catalytic property. Catalytic property. Okay. We know that transition elements are mainly act as catalyst, and it is due to its variable oxidation. It can act as intermediate with the variable oxidation state. And you know the mechanism of catalysis. Okay, mechanism of catalysis. You know the mechanism. There is if this is the catalyst, metal catalyst, bond absorption of your reactant. Chemisorption of reactant. Okay, so your transition metal surface can decrease the or can break the bond energy or can reduce the bond energy of what? Reactants. So transition metal which act as a catalyst. The main reason, what do you mean by catalysis? Catalysis, what is the role of a catalyst in a reaction? I think you speed up the reaction by altering the mechanism. Okay, you know, I think you are familiar with the concept of activation energy. Activation energy, this is energy possessed by reactant molecule. In addition to that, there is an extra amount of energy for forming activated complex. I think you are familiar with that. Activated complex. It is discussed in chemical kinetics. Okay. Already reactant have some kind of energy. In addition to that,
the reactant should absorb some kind of energy to form the intermediate or activated complex or transition state, and that energy is said to be activation energy. Okay, so then it becomes what? A product. This is the mechanism of a reaction. Ready? If you use catalyst, what happen means catalyst bring the reaction through an alternate path. Okay, this is not the path, through an alternate path by lowering what? Activation energy. If activation energy is lowered means the reactant can achieve the intermediate state quickly, so that reaction will finished in a short time. Okay, this is how your catalyst alter the rate or increase the rate of a reaction, by altering the mechanism through lowering the activation energy. Okay, so write some points. First one, most of transition metals can act as catalyst. Most of transition metals can act as catalyst. Okay, write some examples which are discussed in your P block elements. Okay, examples. You know, in Haber process, in the case of N2 plus 3H2 gives 2NH3, which is said to be Haber process, where powdered iron used as catalyst. And in case of Oswald process, I think you are familiar with Oswald process, 4NO plus 6H2O. Platinum rhodium wire gauge used as catalyst. Platinum rhodium, mixture of platinum and rhodium. These all are transition metals, right? Okay. And in case of your contact process, vanadium pentoxide used as catalyst, and this is an oxide of transition metal. Okay. Then Deacon's process for the manufacture of chlorine. Write it. Okay, for the manufacture of chlorine, where CuCl2 used as catalyst. All are transition metal compounds. Okay, so usually transition metals are used as catalyst. Okay. Write down. Transition metal can lower the activation energy by weakening the bonds of reactants
which are adsorbed on the surface of catalyst. Transition metal can lower the activation energy by weakening the bonds of reactant which are adsorbed on surface of catalyst or surface of metal, which means or transition metal. Okay, this is one of the reason for the property of transition metal as catalyst. The second reason, that is transition metal can exist in different intermediate with a different oxidation state. Okay, next point, transition metal can exist as different intermediates in different oxidation state. So these all are mainly responsible for the property of a transition metal to act as a catalyst. Okay, and it can provide large surface area. There is also one more point. Okay, can provide larger surface area. Ready? The next, formation of interstitial compound or interstitial compound. Put it as heading interstitial compounds. Interstitial compound. Interstitial compound. Interstitial compound means? What do you mean by interstitial compound? Interstitial compound small molecules like hydrogen, carbon, nitrogen, like that, which are trapped in the interstitial site. Interstitial site means the void site other than lattice, right? Okay, so we know that all transition metal have a definite close packed structure. Okay, except your zinc, mercury, cadmium, they have some typical kind of structure. All other have either CCP, BCC, HCP, like that. So there is a vacant space or interstitial space in transition metal lattice where it can trap some small elements, and such compounds are known as interstitial compounds. Okay, so write one point. Transition metal can trap small atoms like HCN. Transition metal can trap small atoms like HC, carbon, hydrogen, nitrogen in the interstitial space of crystal lattice. In the interstitial space of crystal lattice can trap small atoms like carbon, nitrogen, hydrogen in the interstitial space of crystal lattice. This is the interstitial space or vacant space or void space. Okay, interstitial space of crystal lattice to form interstitial compound. Okay, no need of interstitial space of crystal lattice. Example TIC Mn4n VH 0.56 TiH 1.73 Fe3H. Okay, these all are interstitial compounds where carbon is trapped in the interstitial site of titanium, nitrogen trapped in the interstitial site of manganese, hydrogen in vanadium. Okay, these all are known as interstitial hydrate. Interstitial hydrate, you are familiar with the interstitial hydrate. Hydrogen is over? No, fine. Hydrate, say hydrogen is trapped in interstitial site of titanium, like in interstitial site of iron. Okay, this all are said to be what? Interstitial compounds. They have some difference. This is the interstitial compound of titanium,
and this is the pure titanium. So we have a comparison between the property of titanium and the interstitial compound. Then what will be the difference? Okay. So next point, interstitial compound have high MP hardness BP boiling point, MP hardness BP, comma density than pure crystal. Okay, than pure crystal. Got it? Is it okay? Titanium carbide have more melting point, boiling point, hardness, density than the pure titanium. Okay, but the ductility, malleability are relatively low compared to pure compound. Okay, next point. But ductility, malleability are relatively low compared to relatively low. Enough. You know what is the comparison. Okay, and they all have same, in pure compound and transition metal have same conductance and chemical properties. The chemical reaction of interstitial and pure compound will be nearly same, and the conductance, they all are same. Okay, one more point. But conductance, comma chemical properties are same as pure compound. Are same as pure compound. Okay. So hardness is much greater, right? Say some kind of boride, boride, SiB3, SiB6. This is said to be borides. Boride means boron is trapped, and this is an interstitial compound of silicon. Okay, like that. In some kind of borides, for example, in the case of vanadium boride, where in some case of boride the hardness is as much as diamond. You know, diamond is most hardness substance, right? So interstitial compound have a greater hardness than the pure compound. Okay, but in the case of some borides, the hardness is nearly up to, or in comparison with the diamond, which means much harder. Okay, that is also a point which is given in your textbook. So write one more point. In some borides, the hardness nearly up to diamond. Okay, one more point and they are chemically inert. Okay, they are chemically inert. Interstitial compounds are generally inert in nature. Ready? Fine. So the next category, complex formation. Complex formation. And you know that in most of coordination compounds, our transition metal act as what? Central metal atom, right? Okay. So first point, most of complex compounds where central atoms are transition metal. In most of complex compounds, the central atom are transition metal. Okay. No need of showing examples. You are familiar with the coordination compounds. Okay. In most of coordination compound, central atom act as transition metal act as central atom. Okay. Because number one, due to smaller size
smaller size, high ionic charge, comma, variable oxidation property or variable OS, oxidation state. And then number 4, availability of d orbitals. Availability of d orbitals. Okay, listen. If you have Al3 plus and Cr3 plus, Al3 plus and Cr3 plus, or if we compare the size of S block elements, S block metals and D block metals, the size is relatively smaller for what? From left to right, size decreases. So comparatively, the size of D block metals are less than what? S block. So smaller size. Moreover, high charge density. Higher the charge. What are the points? Points on the criteria? Due to smaller size, variable oxidation state, high ionic charge. These all are the reasons. High charge density. We know that S block metal can only exist as either +1 or +2. So the relatively the charge density is much low. But D block element can form a higher, as much as possible oxidation state. Okay. So charge density is ionic charge is relatively higher, but the size is relatively smaller. Ready? And availability of d orbitals. Okay, you know that the ligands can form, according to valence bond theory, ligands can form coordinate bond to the vacant d orbitals. Okay, ligands can donate the electron pair to vacant d orbital. So availability of vacant d orbital is one of the reason. Ready? And it can exist, it can show variable oxidation state. Variable oxidation state. These all are the reason for a transition metal to act as, mainly act as central metal atom in coordination compound. Okay. The next, alloy formation. Alloy formation. Alloy formation. Alloy formation. We all know that transition, if you are comparing the size of a transition metal across a period, the size is nearly same, right? From left to right, size first decreases. Okay, so almost all transition elements, for example, iron, chromium, manganese, they all have similar kind of size. Okay, so since they all are having same size, they can be easily mixed to form a homogeneous mixture. That is said to be what? Alloy. What do you mean by alloy? It is a homogeneous mixture of two or more metals. Ready? Why your transition metal can act as transition metal shows alloy property means we can easily mix transition metals or different transition metal, iron, chromium, manganese, they can be very easily mix because they all have same size. So they once they mix, they forms a same shape of crystal structure. Okay, iron followed by manganese followed by iron, like that they forms a well close packed crystal structure. Okay, because their size is relatively same. That is the main reason. Okay, so for alloy formation, first point, alloy is a homogeneous mixture of two or more metals. Homogeneous mixture of two or more metals. Alloy is a homogeneous mixture of two or more metals. Next point. Transition metal can act as or can form alloys. Transition metal can form alloys. In bracket the reason, due to the similar size, they can be or they can easily blend. Due to similar size, they can easily blend. Due to similar size, they can easily blend. Size similar ayadine kondu, they can easily blend.
Blend means mix here. Ready? The next point. Okay, next point. Alloys are relatively hard and having high MP. Alloys are relatively hard and having high melting point. Relatively hard and having high melting point. Ready? Example. Invar. Example. Invar is a alloy, ferrous alloy, alloy of iron. Okay. Invar, in bracket, Fe plus Ni plus Mn plus C. Fe plus Ni plus Mn plus C. Okay, well the composition is, this is nearly 64% and this is 35%. Okay, Invar. The next is nichrome. Where the arrangement of nichrome have nickel, iron, chromium, like that. Okay, where the greater content is nickel. Nickel is around 60% and this is of 25% and this of 15%. Okay. The next, stainless steel. In bracket, Fe plus C. So ferrous alloy containing iron and carbon. The next, duralumin. Simply the composition mentioned means this is an alloy of nickel. Okay, and this is considered as an alloy of Fe. The component with the greater composition simply taken as the parent. Okay, here the parent is Fe, here the parent is nickel. That's why the composition is shown. Okay, the next is duralumin. It's an alloy of aluminium. Duralumin, in bracket, aluminium, copper, manganese, magnesium. Okay. The next, there are some examples given in your textbook. That is brass, copper plus zinc, bronze, copper plus tin, bronze, copper plus tin, German silver, copper plus zinc plus nickel. Brass have copper plus zinc. In addition to that, if it is in addition to that we have nickel, then it is said to be German silver. And these are the important examples. Enough. Example. And some alloys are mentioned in your metallurgy also. General principles. Okay. So that is enough. So that's all about alloy form. One more point. The alloy of mercury with the metals other than Fe and platinum called amalgams. Alloy of metals with the mercury other than Fe and platinum called amalgams. Ready? These all are the important alloys. The next alloy formation, colored property, colored property, colored property, catalytic industry, colored property. Okay. First point, for a transition metal to be colored, for a transition metal to be colored, for a transition metal to be colored, it should have partially filled d orbital, partially filled d orbital, partially filled d orbital. Okay, in bracket, not d0 or d10. Okay, the d orbital should be partially filled, then only the excitation possible. Okay, partially filled d orbital. Example, Sc3 plus, Sc3 plus, Ti4 plus, V5 plus, Zn2 plus, Cu plus. Okay, are colorless. Reason? This all are D0. These two are D10. Okay. But there is an exception or a secondary phenomenon. But in case of, KMnO4, you know the color of the central atom, but manganese is plus an oxidation state, right? The configuration is 3D0, but this have a color purple, right? Have a color purple. KMnO4 have a purple color, ready. And K2CrO4, where chromium is in plus 6, the 3D0 have a, okay, K2CR2O7, orange red color or simply orange crystals, where the chromium is in plus 6, 3D0. Then Cu2O, where copper is in plus 1, it is 3D10, having a red color. Okay. Here the surrounding atom all are oxygen, right? The surrounding atom all are oxygen. And there is a phenomenon what we call as ligand metal charge transfer, LMCT, ligand metal charge transfer. So there is a transfer of here the d orbital is vacant, right? So there is a transfer of electrons from the ligand. Ligand means surrounding species to the central atom, so that it can excite and it can show what color. Okay, so no need of moving to the depth. You simply know the case. So this is a general statement. Okay, these all are some exceptions, or this is due to ligand metal charge transfer, LMCT. Okay, I think this is mentioned in your textbook. Colored property. Okay, leave it. And better to study the colors of some species which is given in your textbook. Okay. Before that, reason for color property. What is the reason for colored property? It is due to DD transition. You know, DD transition. So there is a transition of lower d orbital to electron transition of lower d orbital to higher d orbital. Okay, if you have an electron which absorbs energy, okay, there is a small difference between this energy is said to be delta O. There is a small difference between difference of energy between, this is the set T2G, right? This is EG, T2G and EG. So the electron should absorb a small amount of energy which is corresponds to visible spectrum. Okay, since the energy gap is relatively small, electron have to absorb a small amount of energy. Okay, that's why the energy absorption which is in a visible spectrum. Ready? So it absorbs a light from visible spectrum so that it can excite to the higher orbital. So it shows the complementary color, which means simply it absorbs a color. For example, it absorbs a violet color. Ready? In your VibGeo, if it absorbs a violet color, so from the visible light it absorbs violet color and emits all other color, and they together combine to form a corresponding complementary color. Okay, corresponding complementary color. Ready? For example, if it absorbs a violet color, it can emit nearly yellow or a yellow-green color. Ready? Actually, energy from visible spectrum is enough for the transition of electron from lower d to higher d. Okay, so it absorbs visible light where a particular energy is absorbed, which is corresponding to any color. For example, violet, red, like that. Okay, and it absorbs and the rest of emitted. Ready? If the rest is emitted, they combine to form a corresponding complementary color. So the metal which exists in that particular color, complementary color. Ready? If it absorbs a violet color, it emits all other, in VibGeo, if it absorbs a violet color, it emits all other color. Ready? So, and the 6 colors, right, totally 7 colors, and the rest of 6 colors combine to form a complementary color, and it will be appear on the top of metal, so which seems to be like complementary color. That is actually happening. Okay, so simply the explanation is there is an electron transition from lower d to higher d, what we call as DD transition. Okay, so that is the explanation. So write down point. It is due to colored property due to DD transition. Colored property due to DD transition. DD transition. That is electron excite from lower d orbital to lower d orbital. It may be T2G or EG, that depends. Okay, if it is an octahedral complex, it will be T2G. Okay, that depends either T2G or EG. That depends on the complex, or depends on the complex. That depends on ligand. Okay, it absorb. Electron can excite from lower d orbital to higher d orbital. Okay, by absorbing a particular energy from visible spectrum. By absorbing a particular energy from visible spectrum. Okay, where the electron is excited from lower d orbital to higher d orbital by absorbing a particular amount of energy from the energy from visible spectrum is enough for this transition, because this energy barrier is relatively low. This energy difference is relatively low, so visible spectrum energy is enough. Okay, so it absorbs particular energy from visible spectrum and exhibit its complementary color. Okay, exhibit its complementary color. Ready? Okay, so you can write the colors of some ions given in your textbook. Okay, if you can, study it. Ready? If you can.
now write in a this pattern SC3 plus, TI3 plus, TI4 plus, like that. Okay? So SC3 plus, it is already written as colorless. SC3 plus, you can show the configuration also. Configuration 3D, so colorless. Colorless. Next TI4 plus, TI4 plus, 3D 0, colorless. Colorless. Okay. Next TI3 plus, TI3 plus. What will be the configuration? TI4 plus is 3D 0, then TI3 plus will be 3D 1. Okay. So color is purple. Then V plus, V plus, V plus 3D4. V plus, the configuration is 3D4, blue color. Okay. V3 plus, V3 plus, V3 plus, what will be the configuration? 3D1. 3D1 or 3D2? 3D? V plus, what is the configuration?
3D4.
V plus, the configuration is vanadium. V plus, the configuration is? This is V5 plus, right? V plus vanadium, argon, 4s2, scandium, titanium, vanadium, 3D. V plus means 3D. 3D3, right? Okay. V plus in the 3D3. V plus is 3D3. 3D3, 4s1. D configuration say down. Okay, better to write D configuration because DD transition. Okay, that depends on the electron in D. Okay, so oh sorry, that is V4 plus. It's not V plus, V4 plus. What about V4 plus? (3D1). V4 plus, the configuration is 3D1. The color is blue. Then V3 plus, configuration 3D2. The color is green. Then V2 plus, configuration 3D3, color violet. Once again, V4 plus, configuration 3D1. Okay, color blue. V3 plus, configuration 3D2, color green. V2 plus, configuration 3D3, color violet. Okay, then CR3 plus, 3D3, violet. Then Mn3 plus, 3D4, violet. CR2 plus, 3D4, blue. CR2 plus 3D4 blue. Mn2 plus 3D5 pink. Mn2 plus 3D5 pink. Fe3 plus 3D5 yellow. Fe2 plus 3D6 green. CO3 plus 3D6 blue. CO2 plus, cobalt 2 plus. So the configuration will be 3D7, pink. Ni2 plus, 3D8, green. Cu2 plus, 3D9, blue. Zn2 plus, 3D10, colorless. Okay,
So the most important is category, that is compulsory ആയിട്ട് നിങ്ങൾ പഠിക്കേണ്ട strike just. So the first one, that is TI3 plus. The most important among this category, TI3 plus, CR3 plus, FE2 plus, FE3 plus. Okay, and the last cobalt, CO3 plus, sorry, CO2 plus, pink color, CO3 plus, CO2 plus, and Ni2 plus, or CO2 plus. CO2 plus, you know, blue. Okay, so you know, you have to do questions from this. Okay, then you may realize that which of the ion, where the question is asked from, the color. Okay, so try to study in that pattern, ready, based on question. So maybe the color of some ions may be asked in the previous questions, like that. Okay, that will be most important, that you should study. Okay, these all are given in your textbook. Ready. Next, industrial property.